Day 21, page 622, problem 32. We're looking for the electric field strength at a location halfway between these two charged particles. These two charged particles are 10 meters apart, so the location is 5 meters from each of them. Once again, with point particles and electric fields, you do yourself a big service by drawing the vector arrows. Due to the plus 10 nanocoulomb charge, you will have a field that points towards the right. I'm going to call that E sub 1, because you're always away from a positive charge. And for the negative 20 nanocoulomb charge, there'll be a field to the right, and it'll be twice as big, same distance, twice the charge, but directionally it's towards the negative, so E sub 2. But the shortcut will be, once we have E sub 1, just double it for E sub 2, then add those two because they're in the same direction. It's easy to add those two vectors. Bottom line is, we're looking for the electric field at that spot, which is 5 meters from each charge. So if I calculate E sub 1, well, E is KQ over R. So E sub 1 is 9 times 10 to the 9th, which is the value of K, Coulomb's constant, times Q, 10 times 10 to the negative 9th, nano is negative 9, divided by 5. Oops, I forgot to square that. That's R squared. So that should be 5 squared, KQ over R squared. You calculate E sub 1, it's some number. E sub 2 is double that. So the final answer is essentially triple this answer when you add those two together. And the direction would be towards the right, towards the negative 20 nanocoulomb charge. Now part B, it's asking you for, or I asked you, that was part A. Then I said, okay, find the electric potential at plus 4. So it's the same diagram basically. Let me redraw it. So here we have the new diagram. We're looking for the electric potential at a location 4 meters from the 10 nanocoulomb charge. The electric potential equation, and here we do not draw any vector arrows, it's a scalar. V equals KQ over R. We'll do two computations at that location. We'll do V sub 1, which will be 9 times 10 to the 9th, times the 10 nanocoulombs, 10 times 10 to the negative 9th, divided by 4. That'll be some positive answer. V sub 2 will be 9 times 10 to the 9th times negative 20. It's important now to get a negative answer, or we get a negative answer because it's a negative 20 nanocoulomb charge. It'll be a negative potential. Bigger due to the larger size, but then reduced by a little bit because of your greater distance of 6 meters. So you get those two answers. This first one, V sub 1, will be a positive number. The second one will be a negative number. The final answer will just be the arithmetic sum of those, and I believe the final answer will be in the negative range because the negative 20 nanocoulomb charge, even though you're a little bit further from it, it'll be a little bit larger than the positive electric potential due to the 10 nanocoulomb charge. So calculate those two values and add them up to get the total potential at that location.